Now let's talk about our motivations. We're looking for cost-effective energy production, something to compete with solar and wind energy, not only for consumer end products and electric power purchasing, but also where wind and solar would lack in terms of extreme conditions such as cascaded areas. We're also looking for higher process utilization by using recycled aluminium to produce the hydrogen gas. We're also looking for cleaner hydrogen production by substituting steam reforming and electrolysis. Let's talk about our objectives. We are looking to design and implement a hydrogen-driven system. We are looking to perform theoretical analysis. We have some governing equations to calculate. We're looking to execute the experiment as designed, and finally to calculate cost, time, and equipment needed to operate the experiment.
Our goal is to produce hydrogen. So this is done by reacting aluminum with water. And as mentioned, the outside layer will prevent the reaction from taking place. So we added sodium hydroxide to break the layer and allow the reaction to take place. With methodology, the control class is where the reaction takes place. We tested different parameters, which are the temperature, the effective temperature, the solution concentration, adding salt, and water quality, and then finally the aluminum source. We started with the primer trial. This was the reference. We used it to compare all other trials. It was 1 mole concentration of sodium hydroxide. This was done by dissolving 6 grams of sodium hydroxide into 150 milliliter of water. We did that into 2 steps. We dissolved the 6 grams first in 70 milliliter of deionized water, and then once in a magnetic stirrer. Once the solution was clear, we added the 80. This was done to prevent any losses in the solution concentration, since NaOH is highly water absorbent. So moving to the effect of solution concentration of NaOH, we prepared 3 solutions: 1 molar, 2 molar, and 3 molar. As shown in the graph, the higher the molar concentration of the NaOH, the higher the rate of hydrogen production.
Now we can also see similar trends in terms of temperature as well with the concentration. Note that this temperature is the initial solution temperature added to the reaction. We also know that the reaction is exothermic, so we expect to see slightly higher degrees of reaction. You can see the base trial here in the dark blue, which is our base trial which we compare, and you can see each 10 degree increment of the temperature, we're getting higher and higher reaction rates. Notice that also the overall hydrogen volume did not change as well, but only the hydrogen evolution rate, and the recovery efficiency has also been a function of the temperature, as because the solution temperature getting hotter and hotter, we expect to see more water vapor present in the sample. Note that also the 60 degree solution took only 3 minutes to produce the 115 milliliters of volume of gas. On the other hand, comparing the best trial took around 13 minutes. So there is a substantial difference when using 30 degrees and 60 degrees. We also discovered the effects of salt. Not that in literature we have seen trends of mechanical treatments such as planetary ball milling. In this experiment, we tried to insert the least energy addition to the system. So we did not add any mechanical treatment, only grinding the salt, which was only commercial sea salt. The other solution, the salt, was a mixture of salts, but mainly comprising of NaCl. However, interestingly, you can see that the reaction rate is dropping by half. You can see around 25 minutes reaching the theoretical volume. The recovery efficiency was not overall affected by the salt addition, but the recovery rate has took a substantial.
In all the previous trials, we did use deionized water in our NaOH solution. So in this trial, we replaced the deionized water with tap water. As you can see here, the deionized water have a higher generation rate than the tap water, and that removes that the quality of the water have a high effect on the reaction. And also, as you can see here, they almost have the same hydrogen quantity, got the same hydrogen quantity, and that also improves that we can use tap water in our experiment. In our last trial, we we changed the aluminum type. In all the previous trials, we changed aluminum foil flakes. In the last trial, we changed it to aluminum powder. It's a mix between aluminum powder and magnesium. As you can see here, in the first 40 seconds, they almost have the same hydrogen generation rate. But after the 20 seconds, the aluminum powder generation rate reduced. And this is for two reasons. The first one, that the aluminum powder have a less aluminum mass because it's a mixture between aluminum and magnesium. So the weight of aluminum in aluminum powder is less than the aluminum foil. So they don't have the same hydrogen generation quantity. And also, it could be there's a reaction between magnesium and sodium hydroxide. So the concentration of sodium hydroxide reduced, as you can see here. And now let's move to our prototype and explain the diameter of our reaction vessel. And we also did a 3D sketch of our prototype. As we can see here. As you can see, there's a solar heater here. And this is an optional choice we put it in the design. Because as we mentioned in our results, the more heat the reaction was, the more the hydrogen generation rate. And then we convert this beautiful drawing to real life, as you can see here. There's the reaction vessel, pressure gauge, safety valve for safety reasons, temperature gauge, and this is a multi-filtration system. The multi-filtration system is to filter in the water vapor and the carbon monoxide. As we know, the PEM fuel cell boiling from carbon monoxide, so we got activated carbon and silicon gel. And now we'll move to on.
To discuss as well the reactor in operation, we've seen it here more in life. This is a more close-up picture to the pressure relief valve that if you can see it here, and this is the pressure gauge. I must mention that this pressure valve is set to 6 bar, which is the nominal operating pressure for such vessels. This is also the pressure gauge, which is also measuring around the same area. And more in operation, you can see here the same filtration system. This is the temperature monitoring system in operation. It was essential to have a fast thermal monitoring system. As we know, the reaction is exothermic, so it helped us record each temperature and how it affects with time. This is the drainage valve. In each trial, we have to dispose of the water that has been used, and we can insert new solutions as well. Now I would like to talk about how such a multi-scale, multi-physics problem can be improved as well. As we know, just normal reviews will take more than a semester. So what we'd like to improve is the system equipment for higher efficiency. We can improve filtration against multiple gases. We would like to also discuss the byproducts and how we can study its structure by either XRD or scanning electron microscope. And the feasibility of recycling by NIH extraction or metallic aluminum. We can also try to comply with international standards of safety. ISO 14687 is for the gas purity and how the fuel cell would react, and each contaminant, what is the allowed limits. And finally, fuel cell and what is the electric power production, how much cost per kilowatt hour we're talking here, per kilogram of aluminum, how much we're expecting to produce in kilowatt hours. Now, to conclude our presentation, I would like to say that the objectives that we have set in the beginning of SDP1 have been reached successfully. The data is complying with literature. We are not seeing any off ends. The hydrogen from recycled aluminum is effective and somewhat reliable. However, we'd like to see that the operation is promising and we can utilize. Safety and data collection can also be improved. And further research will improve this experiment and enhance the performance. And we are also looking forward to integrate industrial factors and international standards.